Hey, Kathy,
Yeah?
what's your favorite part of the diffusion equation?
My favorite part is the partial differential aspect.
Are you partial to it?
Yes.
It's no ordinary differential equation.
No, it's no ordinary differential equation. Meet Cecilia, the cell. Cecilia just ingested a calcium tablet. At first, the calcium is concentrated at one particular point, but eventually it will spread out to evenly distribute itself across the cell. But how exactly does the spreading out happen? This process is governed by the diffusion equation, and in this video we're going to go through 3 explanations of how to understand it.
So here U denotes our quantity of interest, T is time, and X is position. The diffusion constant D, we can just pretend it's a number, like 5.
So how do we understand the second spatial derivative?
We'll give 3 different ways of understanding what's going on the right-hand side over here. So this first interpretation uses conservation, which means that the total number of ions within the cell stays constant. So let's break apart this second derivative into 2 separate derivatives. So on the inside, we have a term called the flux, which we use J to denote, and then we take a second derivative on top of that. So flux refers to the net amount of stuff flowing from one side of the slice to the other.
Yeah, so that would be kind of like the net transfer from one chamber to the next.
Yeah. Or to give another analogy, so instead of looking at a cell and calcium ions, we can pretend that the cell is a highway and the calcium ions are actually cars that are just moving along this highway. And the 2 of us are sitting at different parts of the freeway.
And each of us counts cars because we're bored or something. And we count the number of cars going north, and then we subtract the number of cars going south.
So we're taking a difference, and that's where the first derivative comes from.
And if everything is going smoothly, we should end up with the same number. But if there's some sort of like traffic buildup, then we'll get different numbers. And when we compare our results, we're kind of taking another derivative of that. And that would be the second spatial derivative.
Yeah. And so that difference of differences represents the number of cars that are accumulating along this segment of the highway, or the number of cars that are exiting in this general region.
If we were able to watch that whole segment of highway and just counting the number of cars in that segment and looking at how that changes over time, we should get the same answer.
So the left-hand side here, du dt, represents the change in the number of cars in this region, whereas this right-hand side represents the differences that we take, and we should get the same number.
So the second spatial derivative and the first time derivative are 2 sides of the same coin.
Another way we can build some intuition for what this second derivative term is by looking at the finite differences version of this. So remember that U is a continuous function of concentration throughout the cell, but we can approximate it by breaking it down into discrete buckets, as we did in the last case. So let's call one of these buckets n, and the 2 adjacent ones n minus 1 and n plus 1. And the way that we can approximate the derivative at any point is that, remember that it's the slope of the line that's tangent to this function. So we can look at the successive differences between these. So in this case, the first derivative at point n, we can approximate it as u of n plus 1 minus u of n. And the derivative at n minus 1, we can also approximate as u of n minus u of n minus 1. So when we take the second derivative, so now we take the difference between these two, and we get u of n plus 1 minus 2u of n plus u of n minus 1. So let's take a look at what this expression is saying. So if we move this 2 out, we get the difference between the average of its neighbors and u of n. So this term measures the convexity of the function. If it's higher, then it's steeper, and if it's lower, then it's shallower. This matches our intuition from calculus class, where the second derivative measures the convexity or the concavity of a function.
So what this means is that if the concentration at point n is lower than its neighbors, then it should increase to meet its neighbors.
Yeah, exactly. So there's a lot of connections here with also Jensen's inequality. If you have a concave up function, then the value at a point is always going to be lower than the average of its neighbors. Yeah.
That's actually very feels very deep and profound.
Yeah.
Yeah.
That's one of the great things about math. It's just there's so many connections between all these different things that you learn about separately, and you realize that they're all kind of interconnected.
So just now we saw that we're trying to move in a direction that looks like an average of our neighboring bins. Going back to the cell example, though, there's another way we can look at this, which is through giving every particle in each bin a choice when it moves. So this is called a random walk, and for each particle in bin n, perhaps it has a 1/2 chance of moving to the right bin and a 1/2 chance of moving to the left bin. So in this way, if we advance one time step and give all of our particles a choice, what's going to happen if we look at the center bin? Well, all of the particles are going to leave because it has to go to the right or go to the left. The number of particles in the bin is going to go down by u of n. We get 1/2 of the particles in the right bin, which is u of n plus 1, and then we get 1/2 of the particles in the left bin, which is u of n minus 1. So this expression looks a lot like our original expression. In fact, it's just off by a factor of 2. We can also consider different kinds of random walks. So for example, in this one, maybe not all of the particles have to leave. Maybe 1/3 of them can stay. So 1/3 of the particles stay, and then 1/3 go to the right bin, and 1/3 go to the left bin. So in this case, because 1/3 have to stay, that means 2/3 leave. So we get minus 2/3 of u of n, that's our current bin, and then plus 1/3 of u of n plus 1, and also plus 1/3 of u of n minus 1. And this equation, again, is just a scaled copy of the one we just wrote, and also of the original equation. The scaling implies that the spreading out in this case is not going to be as fast as in the 1/2 case where particles are forced to leave the bin.
And I think the really amazing thing about this is that the way that this particle walks doesn't even have to be symmetric for us to get this second derivative approximation.
Mm-hmm.
Or let's say it has a 1/4 chance of going to n minus 2, half chance of going to n plus 1, and a 1/4 chance of staying in its current position. If we do the same computations, then we'll end up with an expression that looks like this, which actually decomposes into 2 similar expressions that we just saw.
So this is like 2 random walks.
Yeah, so this is basically tracking 2 different random walks at the same time. The most surprising thing about all 3 of these random walks is that after a long time, the distribution of calcium throughout the cell will have the same shape, which is a bell curve. And this is true because of a very powerful theorem called the central limit theorem. It needs 2 conditions to be satisfied. So the first is that the expected value of this random walk is 0, which means that we're not expecting more particles to move left than right. The second is that the variance has to be finite, which means that we shouldn't see too many particles move too far from where they originally started. So as long as these 2 conditions are satisfied, in the long run, as we watch all of these particles move around and bounce around, eventually they will all converge on this distribution. One caveat is that these distributions might have different shapes depending on the parameters that we give it, but we'll see the same distribution.
Then we'll converge onto this normal distribution.
Exactly.
Yeah.